Okay, let's get started, please. So, okay, so remember what we're doing? We're talking about line integrals, right? Line and path integrals, line integrals. Right? So these are some sort of generalization of your one variable integral, right? Just like in one variable, you have this thing, you had some function, and you're integrating it over, a line segment. And now what we're going to be doing is integrating over curves, right? So here you have some smooth curve like this, right? Some curve C, right? And that curve is parameterized, right? Is parameterized by some function r, right? So this is r of a. This is r of b, right? And then over that function, over that curve, you have some function, some at each point on that curve, you have some value, right? So f of xy, f of xy, f of xy. And you have all these values that float above this thing, right? And you're interested in basically the area of this fence along this curve. Okay, and what we said was that you could do this by evaluating Riemann sums and then taking the limit of those Riemann sums. Of course, to do so is kind of a pain, and instead, so we write this expression. So this expression denotes the line integral of the function along that curve. Right? So this denotes what's called the line integral of f along C, right? Okay, and it turns out that we can evaluate this by using the parameterization. So you evaluate it by saying, okay, I'm going to take f at r of t, right? I'm going to do a change of variable, basically. And I'm going to evaluate f, right? T is going to go from A to B, right? T is going to go from A to B, right? And I'm going to take, for each T, right, I'm going to map that over. I'm going to get R of T, and then I'm going to evaluate f there. I get some height, f of R of T, right? And then I'm going to integrate that thing from A to B. Okay, that's not going to give me the right thing. If I just integrate that, that's not going to give me the right thing. I need to throw in some sort of scaling factor, right? The scaling factor will be the speed of my point. The instantaneous speed at that point, right? Because the speed times the change in time will give me the distance traveled, right? This is speed. This is change in time, and that thing will give me the time, the distance traveled, the arc length traveled. Okay, so that's how you evaluate it. It's just like the change of variable formulas that we did before. Okay, so for example, and somebody gives you a curve, so C is a curve parameterized by R of T, which is T cubed comma T. 0 goes from T goes from 0 to 2. And somebody says, somebody wants you to integrate this thing, y cubed ds over C. Okay. So what you do is you say, okay, well, I've got my function, right? And I've got my r here, right? So r of t r of t is t cubed comma t, right? R prime is 3t squared comma 1, right? The norm of r prime is the square root of 4t to the 4th plus 1. Right? So you work out the necessary stuff, and you say, okay, so I know, using my change of variables formula, that this is going to be equal to the integral from over the time interval, right? This integral over over the arc length, over the curve, I can express as an integral over the time interval, right? And that's going to be f evaluated at r of t, right? Times r prime t dt. Right, my function was the y cubed function, right? F of xy is y cubed, so this gives this f here is going to be y cubed, right? T cubed 4t to the 4th plus 1 half dt. Okay, and then from there you just integrate. Yeah, Flo?
Can you just repeat how you got from f of t to the 3rd t to just t to the 3rd?
Yeah. So all we're doing, so just note at this point that your function is this function, right? Here's our function, right? Y cubed, right? We're going to take that function and we're going to evaluate it at r of t, right? Right. So we put in, right? We put in t cubed. We put in r of t into f. F says I'm going to take the second variable and cube it, right? So I take the second thing you've given me and I cube it. Okay, so it's t cubed.
So this would be 9t to the 4th?
Yes, thank you. Okay, let me, everyone all right with that? Let me just give you a quick one to do for yourself, just as practice in setting up, right? So C is given by x equals t squared, y equals 2t, as t goes from 0 to 1. Okay, so take 30 seconds and write this down. Okay, sorry, that was more than 30 seconds. What do we get? So I should say that, here we're writing x is t squared, y is 2t. That's the same thing as writing, r of t is t squared, comma 2t, right? That's the same thing. Okay, it's just two different ways of expressing it. Okay. So, okay, so what do you get? Somebody just tell me.
From 0 to 1.
Say it again.
Integral from 0 to 1.
Okay, integral of 0 to 1.
That's 2t cubed.
So 2t cubed, right? So you get xy, right? X times y.
Times 4t squared plus t squared to the 1/2.
4t squared plus t squared to the 1/2. Is that right? R prime is going to be 2t. Yep. 2.
Oh, wait, sorry.
So we get 4t squared plus 4. Okay. Let me make one comment. So one comment. Here's one way of thinking about this formula, right? How do we get this formula? F of xy ds, right? Where s is the arc length. Right? S is the arc length. Right. So recall the arc length function. Right. Recall the arc length function, s of t, defined as the integral from a to t of the speed. Remember way back when we talked about arc length, we had this thing called the arc length function, right? You integrated the speed against time from a to t, and that gave you the length of the arc at time, length of the arc at time t. So if we differentiate this thing, ds dt, right, if we differentiate this thing with respect to t, of course you get right? You get r prime at t. I'm sorry, the magnitude of r prime at t. Right? And so, you know, so the book gives this sort of thing like, well, ds is going to be r prime at t dt, which is not to say that you can multiply through by dt, but you know, this is sort of a justification of how you get this formula. How you get this formula. To me, this is not really a justification. This is more like a mnemonic. Okay, but anyway, so if the book gives this, I think I should give it to. Okay. Okay, so right now we have these integrals over curves. There's also something else. So like this, f of x y dx over a curve. Okay, and in that case, so this is something a little different. The way you want to think is that, again, you have some parameterized curve here, right? You have some parameterized curve here, and again, you have some function floating above it, right? But this time, you're not integrating against the arc length. You're actually integrating against the x length. Okay, so you're integrating. If this is, say, right, if this is your x-axis, what you're integrating against is if you projected downwards, okay, and you took these lengths would be your dx. Okay, right, these lengths would be your dx, right? The change in the x length, not the change in the length of the not the length of the arc, but the change in the x values. Okay, and so this is, you know, if you wanted to get an integral of your function against that, then you would integrate f xy x prime t dt. Dt.
Is that still called a line integral?
It's still a line integral, yeah. It's called a line integral with respect to x. Whereas the previous one was called a line integral with respect to arc length. So let me put an example to make this concrete. Somebody gives you a curve. Curve is a line segment from 0, 0 to 2, 0. And says, I'd like you to integrate this function against x over that curve. I'd like you to integrate the function xy over that curve against dx. So all you need to do is to find a parameterization. So let's make up a parameterization. Here's one. 1 minus t times 0, 0 plus t times 2, 0. As 0 goes from t goes from 0 to 1.
You can just make anything up.
Well, this is sort of like the standard one. This is if you have 2 points, if you have 2 points A, B, C, D, then if you take something like this, then you notice what happens, right? At time 0, it's going to be at AB, right? And then at time 1, it's going to be at CD, right? And this is actually a linear, this gives you a straight line between AB and CD. So this is sort of the generic parameterization of a line segment. Okay, this is the one that I think we might have even mentioned it earlier in this course, but in any case, this is basically what the easy thing to do. Okay, so that's to say, I mean, it's sort of obvious what you should do in this case. Right? You're going from 0, 0 to 2, 0, so why not take something like this? Right. But just to illustrate that, just to give you the general thing that you can use for any line segment.
Would it always be from 0 to 1 then?
Yes.
Okay.
Yes. Because of the way I've set it up. Okay. Okay. So then, right. So then, what do we get? Well, right. So this is going to be the integral from 0 to 1 of x times y. That sort of ends it for us. We don't really need to go on, but let me finish it, just for the sake of form. Right? X times y times x prime dt. Right? This is your x, y, and this is x prime. And if I had something like this, xy dx plus x minus y dy over the same curve, then you do something similar, right? You say, okay, this is going to be the integral from 0 to 1 of 2t times 0 to dt plus the integral from 0 to 1, x minus y, right? X minus y dy, but my y thing is 0 anyway, so I get 0 again. Should choose a better example. Okay, but you see what you have to do, right? Okay, so far we have integrals against line integrals against arc length, line integrals against x, and line integrals against y. Okay. In a second, we'll do something a little bit different, line integrals of vector fields. But first, let me make a few remarks. So one, if C is a piecewise smooth curve, remember that our curves weren't allowed to stop or to have derivative equal to 0, et cetera, right? So you could have something, I have some sort of like shark-like thing in my notes, so I'm going to reproduce it here. Suppose you have something like this, and you want to integrate over this. Well, you just do it in pieces, right? So you just break it, right? Each of these guys is a smooth curve. Right? And then you integrate over each of them. Right? So the integral over C of f x y ds is just going to be the sum of the integrals over each of those pieces. So if it's piecewise smooth, then you just break it into pieces and integrate. Two, let negative C denote C with the reverse orientation. Right. So if C is going this way, right, starts at this point and goes to this point, negative C is going to be the same curve, but just going in the opposite direction. Okay. I'm going to ask you this. What do you think the relation is between the integral over C and the integral over negative C? What kind of relation is there, do you think, between these two things?
Shouldn't they be equal? Because it's just the area.
I'm smiling not necessarily, so I don't mean to give anything away by this slide. How many, just out of curiosity, how many people think it's going to be equal? How many people think it'll be negative, say? Actually, it's actually going to be equal, right? Because if you think about it, what you're getting is, think about what the thing is. It's the area over this curve. Right? It's the area over this curve. I mean, the area of the fence here. Right? Whether or not your fence goes this way or that way, it doesn't really change. Right? You're multiplying. You're taking the height and multiplying by the arc length. Right? So you're going to get this arc length, arc length, arc length. You multiply by the heights, and you get this area. Okay? It'll be the same thing. Yellow.
So would you still write the integral from, like if it was from 0 to 1, that's what the 2 points were, would you still write it as that, or would it be different, like rounded differently?
The parameterization would be different, right?
Okay.
Because your R of t, right, went from A to B, right? t goes from A to B, right? And then you'd have some different parameterization, right, for the reverse guy, right?
But it would end up being the same.
But it'll end up being the same. It'll end up being the same. Okay, second question. What if we're talking about this thing? Again, if you're integrating against x, and you say, now we're going to go in the reverse direction. Is it going to be the same, or is it going to be negative? How many people think it's going to be the same? How many people think it's being negative? It's actually going to be negative. It's actually going to be negative because although these values are going to be the same, when you take the x prime will be going in the opposite direction, right? So the change in x is negative the change of x that it was before, right? So it'll be negative. So one has to be a little careful. Another comment. If we reparameterize C, right, suppose you have some C that's R of t ranges from A to B, right? If we reparameterize C as, say, R composed with gamma of t, then you still get the same integral. Right, so it doesn't matter if you reparameterize. And then the last comment is that one can do this in higher dimensions. Right? If somebody asks you for the integral of x, y, z squared ds over some curve, right? C is a curve in R3. You just do it exactly the same that we've been doing it, right? You take, right, you've got your R, right? R will be a function, R will be a curve in R3, but you just do the same thing, right? You take the derivative of it, you take the absolute value of the derivative, right? You integrate this thing against the absolute value, the magnitude of the derivative dt, and you have an integral. Okay, so it's, you can, it's not, all it is that your curve is not in the plane anymore, your curve is something in space, right? And it's a little bit like, maybe it's hard to see what you mean by a fence, right? The fence is sort of hard to see now. But if you want to have some way of visualizing it, you can think of it as the mass of a wire. You could think of this as density, and then you're integrating density against length, and then the integral would represent mass, if you want to have a physical sense of what the integral means. Okay. So that's the end. Comments? Okay. Next kind of line integral is called a line integral of a vector field. Okay. So here's the setting. You have in space a vector field. Okay, so C is F is a continuous vector field. Okay. And C is a curve in that vector field. smooth curve with parameterization r of t, as usual, t going from A to B. Okay. So then the integral f dot unit tangent vector ds field dot unit tangent vector ds. Right. This thing is the line integral of the function f dot t along C. Right. Is called the line integral of the vector field. Along C. So what we had before, the things that we had before were called line integrals of functions along curves, right? Line integrals of functions along curves. Here we have something called the line integral of a vector field along the curve. Okay, but the line integral of the vector field along the curve is a line integral of a function along the curve, namely this function. So it's just a particular instance of the previous sort of integral. Okay. It's just that you're integrating the function that you get by taking the field dotted against the unit tangent vector. Okay. So it's just one particular instance. Part of the trouble, I think, for students in this last part of the course is that there are a lot of things with different names. Okay. They'll take the line integral of this vector field. Like, wow, what? Okay. Just remember that the line integral of a vector field is a line integral of the function that you get by taking the dot product of the field against the unit tangent vector on the field, on the curve. Sorry. Okay, if I could say it, maybe I can ask you to remember. Okay. Okay. So right, and it's denoted f dot b.r.t. Yeah. So it's sort of problematic because there's a lot of different terms and a lot of notations. There's notation for each of these different terms. Okay. So here is the, when you see this, you say, okay, this is the field, the integral of the field along the curve. What we mean by this is really this. Okay, the integral of the field dotted against the unit tangent vector against the arc length, right? And then you have to remember what that is, right? What is that? That thing is the integral from A to B of f evaluated at r.t, right? Dotted against the unit tangent vector, right? Well, the unit tangent vector is r prime t over the magnitude of r prime of t, and then ds, right? ds, recall, is r prime t dt, magnitude of r prime t dt. Right, so it boils down to this, but you notice that some cancellation occurs, right? And this thing turns into the integral from A to B of f at r of t dot r prime t dt. Right? Justifying the notation that we use. That's why we use this notation. because it boils down to this integral. Okay. For those of you who know physics, this is the work done by the field in moving moving an object along this path. Okay. So work done by F in moving an object along path C. Right. The work done is the force dotted against the change in position, right? And so this is like the sum of all those infinitesimal bits of work. Okay, so for example, somebody gives you a field, f of x, y, z is sine x, cosine y, xz, and gives you a curve, r of t is t cubed minus t squared t, as t goes from 0 to 1. Okay. And if we want to calculate f.dr, well, we see that what we're going to need to do is take the integral from 0 to 1 of f evaluated, right? F evaluated at t prime negative t squared t, right, dotted against r prime t, t squared, negative 2t, 1 dt. Okay. In other words, the integral from 0 to 1 of sine t cubed, cosine negative t squared, xz is t to the 4th, dotted against 3t squared minus 2t, 1 dt. The integral from 0 to 1 of 3t squared sine t cubed negative 2t cosine negative t squared plus t to the 4th dt. Okay, and then you just integrate. Everyone follow what I'm doing? I'm just using using what we worked out over here. Right? The integral boils down to f dot r prime dt. Okay. Question: if suppose we have the curve going in the opposite direction, what do we get the same integral or negative the integral? Do we get the same integral or the negative integral? Who says the same? Who says negative? Sorry.
Wait, is that again?
Sorry, it's negative. You're
Can you explain the difference again?
You're three for 3 now.
Yeah.
Can you explain the difference again between if it's going to be negative or if it's going to be equal?
Okay. The only one that's going to be equal is if you're integrating the same function, right? You're integrating some function ds, right? And if you change it, it's not going to change anything.
Mm-hmm.
All the other ones All the other ones we've done are different. And this one, you may think, oh, but what about this? You've got this ds here. Isn't it the same thing? Well, you're not integrating the same function because the unit tangent vector is going in the opposite direction, right? So you're going to get negative.
Okay, so only if it's just f.
If you're integrating the same function in across the negative curve, then it won't change. Okay. So okay. So last thing in this section. Vector integrals, the line integrals against x, y, and z, and line integrals of vector fields. So to make a connection. So let's say that f of x, y, z can be expressed by three functions: p of x, y, z, q of x, y, z, r of x, y, z. If you look at the integral of the vector field, so you're taking the integral of the vector field over a curve, right? That's going to be integral from a to b, f of r prime t dt, and dot r prime t dt. Right? That's to say the integral from a to b of p of x of t of y of p t of t q x y z r x y z dotted against x prime t, y prime t, z prime t. Right. So if our curve, of course, is x, y. Which is the integral from a to b of p blah 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 x prime t dt plus the integral from a to b of like this. Like this. A to b q y prime t dt plus r z prime t dt, which is p against dx, p dx plus q dy plus r dz. So just to connect the two notations that we introduced earlier, that we've introduced today, right? If you take the first component against dx plus the second component against dy plus the third component function against dz, that's the same thing as the integral of the vector field along the curve. by this calculation, as you see, trivial.